So this is the part 2 of this video, right? So please go and see the first part of the video for this problem 261 graph valid tree, and in which we have already discussed about what is graph and DFS, right? So if you recall the approach 1 of the first part of this video, in which we have gone through the little bit of graph theory and the iterative DFS, right? So in which we have discussed that what is graph, right? So graph is a tree. Graph is a tree if and only if two conditions will meet, right? So it's saying a graph can be a tree if and only if the two conditions will be met, and that we have discussed if graph G is fully connected and if graph G contains no cycle. Means the first example we were talking about 0, 1, 2, 3, and there was one node 4, right? So if we are talking about this tree, right? So all nodes are connected with each other, right? 1 is connected with 2, 2 is connected with 3 is connected, right? Like that, and 4 is connected with 1. So all the nodes are connected with each other. So the first condition is satisfied, G is fully connected, and G contains no cycle. This graph doesn't have contains any cycle. If it will go like this one, right? So this should not be happening, right? So these 4 to 2 should not be connected. Like it will connect 4 to 3, so this should not be connected, right? And that's why we can say that G contains no cycle, right? Because it is not making the cycle, right? So this graph contains both. First is not fully connected, and second doesn't contain any cycle. So both two conditions are meeting, right? And so that we can say that this graph is a valid tree, and that's why the first example is giving true. In the second example, can we go here? Let's see. Yeah, we can go here. So this graph G is connected with what? All nodes are connected with each other, correct? And that's why it is not making any cycle also, and it's returning so true as a value, right? As you can see this graph. And when we are talking about what? This graph, right? So it contains it connected with each other. All nodes are connected with each other, but it maintains a cycle. That should not be the case, right? And that's why it is returning false. Got it? Now we have understood the graph. Graph should be have two conditions. The first, if the graph is fully connected, and if graph is not connected, right? These two conditions. Now think about depth first search, right? So depth first search is a classic graph traversal algorithm, right? So this DFS that can be used to check both two conditions. The first that we are talking about, graph G is fully connected, and another graph contains no cycle. So these two conditions can be used, right? Can be tested through depth first search. How? The graph G is fully connected if and only if we started a DFS depth first search from a single source and discover all the nodes in G during it, right? We will pass the source like index 0, node 0, then we will move to all the children 1, 2, 3, and from 1 we will go to next what? 4. Like that we will go, right? So with the help of DFS, we will pass one single source and we will discover all the nodes in G, right? That will also help the DFS algorithm to traverse in all the nodes in the graph. Now, if we'll talk about the condition second, G contains no cycle. So if and only if the depth first search never goes back to an already discovered node, right? If and only the depth first search never go back to already discovered node, right? And there is only one thing that we have discussed, that we need to be careful not to count trivial cycle, right? Trivial cycle, how it will form? So A points to direct to B, right? Give directed as A to B and B again going to A, means like this. It maintains cycle like this, right? So we have to take care of that thing, right? Now if you talk about the iterative depth first search, right, in which what we have seen, we have taken the parent key, right, parent map, and in the parent map we are maintaining all the nodes, and then we were checking the if the neighbor node is going to the parent is having in the parent map, and if not, if have, then we will return false. We are not going to do anything, and we will return false. This graph is what containing, and so it is not a valid graph, valid tree, right? Let's go to the code section and we'll do the hands-on. We are talking about, we have taken what, the parent node, right? And parent node, initially what we did, we have put into the first node we have put into the parent, and we said that it doesn't have parent, right? Means the node 0 doesn't have parent, that's why we are putting -1, right? And then we have taken the stack, and then we were passing we were pushing the node 0 onto the stack. Then we have started what, while loop, and then we are taking that node, and we are getting all one by one neighbors of that node, and we are checking that neighbor node into the parent map. If that node contains already, then we will continue, right? Otherwise, if it contains, then we will do what, we will say this key is already in the on the node, and we will say it's false, and then we will check what, stack.push to maintain the record, right, key that we have pushed or not, right? And another thing, parent, we have to put the parent in parent also, stack and stack node, stack and onto the map, both pair we have to put. And finally we'll check if the size is equal, parent size is equal to n, right, is equal to n, then means it is valid tree. If not, then it will not, right? So this is our iterative depth first search, in which we have taken parent node, and for each node we'll check it should not go to its parent, right? That was the thing. If it goes back to parent, it means it's not valid tree. Now alternatively, you could use recursion as long as you are fairly confident with it. Okay, now the recursive approach is more elegant, and but it considered inferior to the iterative version in some programming languages like Python. Okay, so this is because the space used by the runtime state vary between programming languages. But on the plus side, we can use simple scene set and just pass the parent parameter. Okay, so this will make code little bit simpler. So if you want to see that, let's go to here and we will update here. Okay, so what we have here, we have the adjacency list, right, this one, and then we will take it as a class member, right? So now what we can say, we have to update this, right? Let me remove this comment and we'll start from here. Now what we have to do, we have taken the adjacency list, and then we will take a set, right? We have not taken any set here, right? So we will take set, and that set is what, if you will take this one as a private, so we should also take private. Let me zoom a little bit, right? Yeah, so we will take a private, then we will take set, and this is what, integer, this is our integer, right? And then we will say sing, and then we will say equal to new as set. Like this we will do. Now this is the boolean function. It will return boolean true or false, tree is valid or not, graph is valid for tree or not. We will pass. Then we will do what? We will check one condition first. What? We will take if this edges that we are passing, all the edges array, if edges dot length equal to what? It should not be equal to what? N minus 1. If it is equal to not equal to n minus 1, means what? It has not traveled all the node, right? And so we can say that it's false. Now you can see that we have initialized the adjacency list, and then we will maintain our adjacency list, right? Finally, we will not do anything here, right? We don't need to do anything. Only we will remove this code, right? And we will do here what? We will say if size is equal to what? N, but not the parent. It is scene. Okay. If scene dot size equal to what? N, and we will maintain one more condition. We can say the condition can be what? We'll take a DFS utility method. We will say that this is DFS, right? And we'll pass 0 minus 1, and we will make this function. We will make a recursive function, and that recursive function will start from what? The starting index, that is 0, and it doesn't have any parent, right? So we will return true if no cycle were detected and the entries graph has been reached, right? The last entire graph has been reached, means we have completed all the nodes. So this DFS utility method will take what? Return type is boolean, true or false. Will take DFS, and it will take first the node. We are passing first node, that is 0, right? This is our node, and its parent. Its parent is what? Minus 1 for the index 0. Now we will check if scene dot contains, right? If scene contains this node, it means what? We have already traversed, and we will say that it's false, right? Means graph is not valid array. If it is not seen, then what we will do? We will maintain our scene, and we'll say scene dot add, and we'll do what? Our node we will pass that we are traversing, so that we will have the record. Now we will maintain for loop, right? And then we'll go to all the node of 0 node, right? All neighbors, you can say. I'll take neighbor, right? All the neighbor will go. How will go? One by one. Each node will go from what we have on the adjacency list, and it will pass the node in the adjacency list, right? It will do get, means we can get all the adjacency nodes, right? Now if we will have our node neighbor nodes, right? So what we'll do, we'll check in the condition if we have parent, if the parent not equal to what? Not equal to the neighbor, one by one neighbor. All the neighbor will check of that node. Not equal to parent means neighbor is not having parent, right? It's not going back. Then we will take a boolean result, boolean, and then we'll pass what? This is our result, you can say, and we will have to do recursive call for the DFS. and then we will pass what? You see our neighbor, all the neighbor will pass one by one. If 0 have what? 0 has the first it will go to its neighbor 1, then 2, then 3, right? In the first example. So it will go for first 1, for 2, and the next 3, right? So all the node it will go, and the node is what? This time this node is parent. So parent is, now if we'll talk about this is 0, and first time it will go 1, next time 2, next time 3, next time 4, right? 4, not 4, when we will pass 1 as a parent and neighbor is 4, then it will go to the next time 4. So this will return your result, and if not equal to what? Result is not true, means we will return false, means the given graph is not valid, right? And after this for loop we will return true. If that is not the case, then we have to return true, right? Let me repeat again what we have did here. We are doing not iterative approach, this is our recursive approach. Okay, this is not our iterative recursive DFS, right? So the recursive DFS, what we have to take? We have to take two things, for the adjacency list and one another is hash set, right? And we will first check what if the edges of the length is not equal to n-1, means we have a invalid graph, right? Graph is not valid for the tree. Then we will initialize our adjacency list, and then we will put all the values of the adjacency list, and we will maintain our 2D array of the adjacency list, right? Now recursively we will call the DFS method, and it will check its all children. So if DFS subtractive method, so first we will pass index 0, node 0, and node 0 will pass and its parent, because node 0 is the root and it doesn't have the parents, and that's why we are passing what? -1 as a root. Next time when it will go, right? So now parent will be what? Not -1, is 0, and its neighbor is what? 1, 2, 3. So first it will go with 1, 0, 2, 0, 3, 0, and after completing that level we will have another one more level for 4, 4, right? And that will, it will go to what? Parent will be 1, but the child will be 4. So 4, 1 we will pass, right? And how we'll do that? We will do here the recursively, that will go to the all children. First we will get that node, and we'll check if it contains in the scene, means we have traversed already, we will return false. If not this case, then we will maintain scene. Otherwise, I told you, first we will pass node 0 here, and we will get all its children 1, 2, 3, right? 1, 2, 3 neighbors we will get. We will check parent, that is -1, is equal to its 0, 1, 2 or 3, right? If that is not the case, it's not maintaining, then what we will do? We will pass first its first neighbor, that is 0, and its parent node is what? Now its parent node is root, that is 0. You pass 1, 0, next neighbor is 2, 0, we will pass 2, and 0 is its root node, right? Alias 3, 0, then it will traverse, and then we will maintain. If anyone is giving false, means we have to return false. And finally, if all neighbors doesn't have like that, if all neighbor is not visited, then we have to put into the scene, and then we will return finally true, right? That's all we have for today. Okay, we will see the another variant of how we will use the iterative breadth first search, and we'll record the breadth first search and depth first search, which are almost the same algorithm, but just with a different data structure, right? So you can try. I'll give you the hint that the first example that we have did for this problem in the part 1, you can use in the place of stack, you can use queue, right? So I'm giving the hint. Please do practice, and please ping me in the comment box that you have completed, and you will send the code also. Okay, and please also comment the complexity analysis. What is the complexity analysis for this program? And if you're not able to find, I'll continue with that part of the video. In the third part of the video, we will see the complexity. But before going to the third part of the complexity, I'll recommend you to please go and find the complexity. I'll give you a hint, like you can take E as the number of edges and N is the number of nodes, right? So what is the time complexity will be, right? And space complexity. Please go do little practice, and please comment that complex analysis for this program and the previous one also. In the next part of the video, we'll see using the queue, right? And also we can do the other approach that we can see iterative depth first search, right? And we'll do the hands-on with the iterative DFS again. We will take another approach, right? And we'll discuss about recursive depth first search also, and we'll see how we can maintain the DFS and we will not pass the parent. We still we are passing what parent, so that we cannot go back and do this. So in this video, we are going to start another approach, that is iterative BFS. Okay, in which we will iterative BFS. Okay, in which we have already seen with the stack route, we will use here queue. So in the place of a stack, what we can do here, we can take queue, right? So and rest of the thing will remain same, right? What we can do here, we'll take stack here, right? How we'll do that? In the place of set, we will, let me remove the whole code and we'll start again. So we are here, we can take this line of code, right? This line of code will work, right? And this BFS we have to remove, right? DFS code. So this line of code, it will work. Okay, now you can say we are going to do BFS. Okay, so in the BFS, what we have to do, we will take we will check first these edges not equal to n-1. If edges are not matching, if edges are not matching, it means what? The graph is not valid, okay, for the tree. So now we have initialized all this adjacency, and this one you know already, this one, right? Now we'll do this later. First let me remove the recursive function DFS, this one, because we are doing BFS, right? Now we have make the adjacency list here, and we have maintained its value into that. Now what we will do, we will use queue. What we will use? We will use queue, right? Like this we will write, and then we'll say it will take what? Integer, all the nodes it will take. So that is our, we'll say queue equal to what? We'll take new linked list, we can take linked list, and this is our queue. Now we have to maintain our scene, right? So what we will do, we'll take the set, right, and we'll say integer scene equal to new has map, right? Let me zoom a little bit. Yeah, like this we will do. Now what we should do, we have the queue, right? Then we will do queue dot offer, and we will add first root node, that is our 0, correct? So once we added the on the queue, right, we have to maintain our record that we have already seen this node what? 0. The first node is we have already done. After that, what we will do, we'll go to all its neighbor. If while till while queue dot is empty. If it is empty, not empty, then we will go to the queue and we'll get one by one its node, right? What we will do, queue dot poll, we will remove from the queue and we'll say that this is our int node, right? This is our node. And now you have the node, then we will go to its all neighbors, right? What we'll do, we'll go to its all the neighbors. How we'll go that? We will make a loop, for loop, right? And we'll say that the neighbor is NEIGHPOUR. We'll say the neighbor is what we'll get from what? Adjacency list. Where is the adjacency list? This is our adjacency list. So we should always take adjacency list, right? We have not initialized the adjacency list here, right? So what we will do here, we'll take here adjacency list. Adjacency list is what? Type of list of list, right? List of list. ls, okay? List of list will say, and this is nothing but our integer, okay? Equal to what? New array list, we can say. This is done, right? Now what we have to say, we are at here. So from the adjacency list, we'll pass our node this dot get, and we'll pass what? Our node. So all its neighbor will come here one by one. Each neighbor will go one by one, right? Now we will make one condition, if condition, and we'll see that is it in the scene, right? If it is in the scene, then it means we have already traversed, right? We have already traversed this neighbor that we are talking about one by one. We are getting all the neighbors of the node, right? And that is what? Neighbor. If it is contains, right, means we have to continue. We have to continue. Now we have to maintain our scene. So what we will do? We'll do scene dot add, right? And we will add on or add the all its neighbor one by one. Okay. Now neighbor is added here. Now what we have to do? Now we know that we have to add onto queue also. Then we will do queue dot offer. We'll add our neighbor onto the queue also. So we have updated both. And finally we have our scene. If scene is equal to n, then we will return to that this graph is what? This graph is tree, valid for tree. Okay, let's go back and we'll see that what we have did. We have taken adjacency list. We'll check all the edges not equal to n-1, then we will return false. Otherwise we'll maintain our adjacency list here. Then we'll take the queue and we'll add on to the queue, and then we'll have our set scene. So we'll put all the visited node here on the scene. If queue is not empty, then we'll remove from the queue, and then one by one node we'll get, and for all the nodes, right, we'll get all its neighbors, and we'll check all the neighbors. If neighbor contains on the scene, then we will continue and we'll add on to our what scene and offer. Okay, let me run this program. So set integer scene has set. Why it is not taking? Cannot type. Oh, sorry. Has set we have to take, right? Has set, not has map. Yeah, this working. Let me submit. Okay. So we have seen what? The iterative BFS, right? In which we have won all its node, right? So if you'll talk about the complexity, right? So please ping me in the comment what is the complexity. Other I'll put into another part of this video. I'll say that the complexity. Okay.